second part of section 4.1, we took a look at long division polynomials, where we can use long division anytime I have a polynomial divisor. And then what about situations where my divisor, again, we got the dividend, and then we have the divisor. When my divisor is both linear and binomial, then I can use this little doohickey right here called synthetic division. It's a great way of doing division of polynomials with binomial linear divisors. It's a little faster. It's doing the same thing as long division, it's just we're eliminating the use of the variables themselves. So here is our process by which we do long division. First thing we do, as we did in long division, is we arrange everything in descending order, highest power to low power, include zeros for any missing terms and constants. Then we would set up, notice what we've done is we've only used the coefficients of this polynomial. And then we're using the opposite of the constant term in the divisor to create the synthetic division problem. So inside of this bracket we have the coefficients of the constant, and then the outside of the bracket we have the opposite of the constant term of the divisor. So we next would, and it's always going to be this process, this never changes. The first thing we do is we drop the very first term. So that 3 drops down and becomes the first number within our quotient. And then the process proceeds as follows. We multiply the constant from the divisor with the dropped term. We get a new product. So we're taking the divisor constant, we're taking the dropped term, we get a product of 6, and then we add those two together, and then we get this 12 here. And now we repeat that process. Take the 2 of the divisor, multiply it by the 12, get a product of 24, add the product of 24 to negative 10, get a 14. Do that again. 2 times 14, 28. Add the 28 to the 7, get a 35, and that then becomes my remainder. So remember, with synthetic or with long division, we ended up with a quotient. And we end up with a quotient here, it's just we don't see the variables. So we had a third degree polynomial that we started with, right? It was 3x cubed, 6x squared, and we were dividing by a first degree polynomial. So if you just go back to your properties of exponents, if I have a third degree polynomial divided by a first degree polynomial, we know that that's the same thing as subtracting their exponents. And we end up with an x squared. And so that's where this thing comes from. That's a 3x squared plus a 12x plus a 14 with a remainder of 35. So that's the synthetic division process that we're going to follow for these next examples. So let's try it for this one. Looking at my polynomial, I have a 4th degree. I have no 3rd degree. So I have 0x cubed. 2nd degree, 1st degree, constant. So we're going to set it up as a 2, 0, negative 6, 3, 5. And my divisor, I'll be considering a negative 2 out here. So we drop. We multiply. Negative 2 times 2. Get a negative 4. Put the negative 4 underneath the next term. Now we add them. 0 plus negative 4, negative 4. Multiply once again. The negative 2 and the negative 4. So these two now multiply. And we get an 8. And then a negative 6 plus an 8 gives me a 2. And we repeat this process. Negative 2 times 2 is negative 4. And 3 minus 4 is negative 1. And negative 2, and again, negative 2, I'm always using this one. Negative 2 times negative 2, negative 1 is 2. and 5 and 2 is a 7. So now this becomes my quotient, and this is my remainder. So I have 2x cubed minus 4x squared plus 2x minus 1 with a remainder of 7. There's my new quotient and remainder for those two polynomials working with each other. What else can we do with the synthetic division? We're actually going to take a look at this in the next part, but here's a little introduction. What if we wanted to evaluate a polynomial f of x, which equals 2x to the 4th minus 6x squared plus 3x plus 5, when x is equal to 2, negative 2? Meaning, what would the y value be if I plug a negative 2 in here? Well, here we are in this process right here. We're showing the generic way that we probably would have done this prior to doing synthetic division. We would have just plugged negative 2 in for all the x's, and we found out, hey, we got a 7 at the end. Well, that's what we had here. There's that 7 at the end. So we're doing this as an example from the same one. And so this introduces us to a remainder theorem here. And the remainder theorem says when doing synthetic division, the remainder that you get is the y value of your polynomial given a value of x. So when you are plugging in some, again, thinking of opposite, plugging in the opposite of this constant value, that's your x. The answer that you get would be the y that would be equivalent to that. And that creates my ordered pair that I can use, again, future, for graphing this polynomial. All right, and we just saw how when we did it with synthetic division, we got the same thing. So synthetic division, again, another way of evaluating a polynomial given some value of x. So let's try that with this next one here. So looking at our polynomial of x to the 3rd minus 7x squared plus 3x minus 2, I don't have anything missing. So I have a 1 coefficient for my x cubed, a negative 7, a 3, and a negative 2. And then because this is a negative 2 as my divisor, I'm going to have 2 out here. So drop and multiply, add. Multiply, add. Multiply, add. So what this means is, dividing wise, I'd have a quotient of x squared minus 5x minus 7 with a remainder of negative 16. Evaluation-wise, what happens if I plug a 2 into that? I would get f of 2 would actually equal negative 16. Then point, what coordinate did I just find? Well, function notation gives you a coordinate. So 2, negative 16 would be the equivalent point that results from that. So I can get all kinds of information just from doing this synthetic division. All right, let's try another. Again, checking for order and checking for missing terms. Now this one I have a 4th degree that's missing. I have a 2nd degree that's missing. So I'm going to have to make sure I include zeros in my synthetic division problem. So 2, 0, negative 6, 0, 3, negative 5. And I'm going to use a negative 2 as my divisor. So drop and multiply. Multiply and add. Multiply and add. Multiply and add. Multiply and add. Negative 4, 8, 8 minus 6 is 2, negative 4 and 0 is negative 4, 8 and 3 is 11, negative 22 and negative 5 makes negative 27. I have as a dividing quotient remainder answer, I'm going to have 2x to the 4th minus 4x cubed plus 2x squared minus 4x plus 11 with a remainder of negative 27. Room here. Try that again. 2x to the 4th minus 4x cubed plus 2x squared minus 4x plus 11 remainder negative 27. Evaluating, what happens if I plug f of negative 2? I get negative 27, which means I have a coordinate of negative 2, negative 27. That's my point. So that's synthetic division and one of its uses.